Okay, today in Math 10C we're going to look at topic 6.6, the general form of the equation of a linear relation. This is going to be in two parts, and here's part A. First of all, it says the general form of an equation. Let's make connections. A softball team may field any combination of 9 female and male players. There must be at least one female and one male on the field at any time. What are the possible combinations for female and male players on the field? Well, if we made a chart with male and females, we could say that if there was one male on the field, there must be 8 females. If there was 2 males, there must be 7 females. And there would go on down like that for 3, 4, 5, 6, 7, and 8 males to 6, 5, 4, 3, 2, and 1 females. So that is a list of all the different possible combinations of male and female players that can be on the field at the same time. In constructing your understanding, Holly works in a furniture plant. She takes 30 minutes to assemble a table, 15 minutes to assemble a chair. Holly works 8 hours a day, not including meals and breaks. Make a table of values for the possible number of tables and chairs that Holly could assemble in one day. Well, tables and chairs, one isn't going to be dominant on the other, so you could put it in either order. We're going to do it both ways. And the first way we're going to do it is with tables first, chairs second. Now, it takes 30 minutes to assemble a table, and that would be half an hour. There's 8 hours in a day. So that means that she could make 16 tables without making any chairs. So one of my combinations would be 16 tables and 0 chairs. Now, if she only made 15 tables, that would leave her half an hour left. And since it's 15 minutes per chair, she could now make 2 chairs. Or if she did only 14 tables, now she could make 4 chairs. Now we're going to follow that same pattern all the way down to 1 table. That would be 30 chairs. And if she made 0 tables, she'd have enough time in a day to make 32 chairs. That's a list of all the possible combinations. Well, we're going to graph this data. Well, we can do it on graphing technology, or we can do it on pencil and paper. I'm going to do it on pencil and paper, of course. What you're going to see is that the number of tables is going to be on the left or on the horizontal axis, the x-axis. The number of chairs is going to go on the y-axis. If you plotted those points, the first one, as you can see, is when x is 0, y is 32, or 0 tables, 32 chairs. Next, I have 16 tables and 0 chairs. That's the other axis. And in between there I have combinations. Notice that this is not a continuous graph because you cannot make 1.5 chairs or 2.5 tables. So therefore each dot represents a possible combination that we can make. Next it says what type of relation have you graphed? Well, this is a linear relation. And how do I know that? Well, there's going to be a constant rate of change between each point. What do the intercepts represent? Well, the y-intercept is where I'm making 32 chairs and no tables. And on the x-intercept, I've got 16 tables and no chairs. In between those 2 points is a combination of chairs and tables. Choose variables to represent the number of tables and the number of chairs and write an equation for your graph. Well, we could say 15 minutes for every chair plus 30 minutes for every table would have to add up to 480 minutes because 8 hours in a day times 60 minutes in an hour means that she's going to work 480 minutes in a day. I can divide everything by 15 and I'm going to get c plus 2t is equal to 32. And then I can also change this into x and y. And since the tables is x and c is y, we can say y plus 2x is 32. And if I subtracted 2x from both sides, I will get y is equal to negative 2x plus 32. I could also do this another way. I could find the slope and the y-intercept. I know that the y-intercept is at 32, so if I used the slope formula, the change in y over the change in x, notice that it goes down 4 over 2, so the slope is negative 2, and b, the y-intercept, is going to be at 32. So again, the equation is y equals mx plus b, or y is negative 2x plus 32. The same as it was in the first graph. Suppose you interchange the columns, and then you graph the data. How would the graph change, and how would the equation change? Well, if we did it differently, we could say that the tables and the chairs could be interchanged. Now we're going to have chairs on the x, tables on the y. Chairs comes first and then tables. And if you plotted the points, you could end up with 16 as your y-intercept and 32 as your x-intercept. Now when you figured out the equation of this, it's going to be y is equal to negative 1/2. And my y-intercept is at 16, so I could say y equals negative 1/2 x plus 16. So the equation does change. This graph is described by the equation 2x minus 3y is equal to 12. The equation 2x minus 3y equals 12 is written in standard form. The coefficients and constant terms are integers. The x and y terms on the left side of the equation and the constant term is on the right side. We may move the constant term to the left side of the equation, and if we did, we would get 2x minus 3y is equal to 12. Subtract 12 from both sides, and you would end up with 2x minus 3y minus 12 is equal to 0. And now we have an equation that's in general form. We're going to stop there, and we're going to take the rest of this into part B.